Bene, buongiorno e un benvenuto anche da parte mia a tutti gli intervenuti che vedo sempre con soddisfazione più numerosi. Io sono Elio Poma e sono il moderatore di questa mattina. Ricordo che avremo questa mattina come da programma 5 interventi e ricordo anche ai presenti la possibilità a fine della prima sessione, intorno alle 12:30-13, di proporre domande e quesiti ai nostri relatori depositando il quesito nell'urna che vedete al centro della sala. Non mi dilungo oltre e vado a presentare il primo speaker, che è uno speaker storico del JTF, nonché grande collaboratore di Legor, Joerg Fischer-Buehner. Il dottor Joerg Fischer-Buehner ha ottenuto il dottorato di ricerca in fisica, metallurgica e tecnologia dei materiali presso l'Università RWTH Aachen in Germania. È stato responsabile della divisione di metallurgia fisica dell'Istituto di ricerca sui metalli preziosi della chimica dei metalli FEM. Attualmente lavora come consulente per Induterm e Legor. La sua ricerca si focalizza sulle proprietà delle leghe per metalli preziosi e sulle relative tecnologie di produzione, con specifica applicazione nei settori orafo, dentale ed elettrico. Il titolo della sua relazione è Migliorare il proprio processo di microfusione. Questa memoria si sofferma sugli aspetti del processo di fusione che più di altri tendono a provocare difetti visibili solo dopo l'applicazione della finitura e controlli qualità, ma la cui formazione dipende dalle condizioni di processo generale. L'obiettivo di questo studio è analizzare i difetti di fusione più comuni e le potenziali cause e fornire consigli utili per evitarli. Prego, Joerg.
Right. Thank you very much, Emilio. Yeah, thank you, Massimo, and the organizers of the JTF for organizing this important event and for allowing me to speak here. We have organized, or the organizers have decided to start the JTF this year with 3 papers more on basic topics, more like training papers, and the 2 further ones will be on galvanic applications and mechanical working, and this first one will be on the casting process. You will agree that improving your investment casting process is a very generic title. We could talk all day about defects and how to avoid them. Actually, we do that sometimes. This presentation is generated from training material that we presented, prepared many years ago for training events around the world to our clients and sales partners. And we just talk about one aspect today, mainly about porosity. So yes, the complexity of the casting process is well known, I guess. It starts with the materials that we use, the waxes, the investment material, the alloy. We put it in a casting equipment and we run the process using a set of process parameters. All these aspects interact with each other in a complicated way during the casting process. So chasing the source of the defects is not always so easy. What we have to do if we want to be economic and if we want to increase the quality of our products. On this slide, you just see a selection of typical defects, starting with some examples for porosity on the left side, over cracks and non-fills, discoloration on the surface, can be tarnishing, can be fire stain, spots are common. So all these are possible defects that we could also look at in later on in other seminars. Now we will entirely focus on porosity. And it's about differentiating between different types of porosity. Yeah, if you want to avoid porosity, you must identify different types of porosity. You must understand the characteristics of them and the major reasons before you can tackle them and try to avoid them in the daily routine. So this will be the sequence that we will follow. First of all, a general comment: if we talk about porosity and pinholes on an air-scarce surface, In many cases, we can trace them actually back to wax defects. So the first recommendation will always be, if you have issues with porosity or pinholes on your surface, check the quality of the wax. Many cases, we can find porosity already on the waxes. They can be micro pores, as seen on this photo. It can be bigger pores. Also, resins that now are generated by the printers that are out there can have defects. So check the quality of these items before you go into the casting process later on. Yeah, differentiating between two main types of porosity is important. We can say, in general, we have two different types: gas porosity characterized by spherical pores, and we can find irregular shaped pores like on the photos on the right side, which we refer to as shrinkage porosity. These are the main two types of porosity that we can find. They will interact and overlap in the real world, but it's good to differentiate them clearly here for today. So what is shrinkage porosity? It's related to the shrinkage of the metal when it solidifies. Here in this graph, you can see the volume of the molten metal that reduces if temperature is dropping, and then there is a sudden drop in volume when the metal solidifies. So this drop in volume is around 4 to 6% for gold and silver alloys, to give you an example. So it's significant, and you can see it on the surface of an ingot very clearly, like you can see here. If you pour just the metal into a mold, you can see a sinkhole. The solidification will start from the edges of the mold and will progress into the inside. And due to the reduction in volume during solidification, we can see a sinkhole, a pipe, a cavity immediately on the bottom here of this ingot. In jewelry casting, the porosity will be distributed in a different way, or in any casting process that involves more complex solidification processes. So the irregular shape that we see in shrinkage porosity items is related to the way the crystals grow, like the branches of the tree that you can see here on this photo. And when these branches of the crystals grow, the metal shrinks in volume and you will have voids. And if metal can feed these voids, then porosity can be avoided. But if this doesn't work well, as we can see on the right-hand side of the picture, I have a laser here, which is good. If this feeding of these voids doesn't work well, these voids will remain, and we have these typical irregular shaped pores, shrinkage pores. And on the left side, you see a micrograph where the microstructure has been etched. We can see also these crystals here. Yes, you can see some microvoids here, but all in all, the feeding went better than on the right side, and we can avoid shrinkage porosity. So how this is done in practice? In industrial castings, like you can see here, this is the cast that's going to be cast. And you see these green items here. These are feeders that are put on typical sections of the cast part, and they will supply molten metal to the casting and feed the casting with liquid metal during all the process to avoid shrinkage porosity. In our jewelry casting, how does this work? We have a main sprue and we have gates or feed sprues. And yes, the task of these parts of the casting is to supply the molten metal during the filling process. And the second task is to feed the solidifying part during the solidification process in order to avoid or minimize shrinkage porosity. So the way of sprueing is very important. Here's just a very generic example. We have a ring and we have a heavy part of the ring here. We put the sprue on the opposite side, and this asks for problem. So this part of the casting may solidify first before the rest of the casting. So when this is solidified, no molten metal can be fed into the other part of the casting. So this will ask for shrinkage porosity in this part of the ring. Just opposite, if we put the sprue on the more heavy part of the ring, solidification will start here and progress entirely into around the ring shank. So this will allow molten metal to feed the solidifying part of the ring and will minimize, or in the best case, avoid shrinkage porosity. Yes, many years ago we focused a lot on computer simulation. So you can see a video here. Let me stop it, yes. So now you've seen molten metal pouring inside. The tree and the parts have completely filled. You can see a temperature scale here, and the metal will start to solidify around 900 degrees. This is an example for sterling silver, and will solidify around 780 degrees. And if you let the video run, you can focus on some particular points of this simulation video. For example, on this ring here, where we have a tiny sprue opposite to the more heavy section of the ring. And I don't know if you can clearly see it now with the illumination that we have here in the room, but you will be able to see that this part will get cold now, so this will ask for shrinkage porosity in this area. Now, just opposite to that, if you have the sprue thicker, bigger, and more positioned on the heavy side of the ring, this will work much better. Solidification will progress in this way, and this will be the best case to avoid shrinkage porosity. So just a guideline, check the sprue system if you can identify shrinkage porosity on the polished surface. Yeah, think about the alloy properties. Some alloys are more prone to shrinkage porosities than others. Typically, sterling silver is less prone to shrinkage porosity than most gold alloys. Within the gold alloys, the higher melting ones, palladium white golds, are more susceptible to shrinkage porosity. And then the very high melting alloys, platinum or palladium based, are even more critical. So what can you do? First of all, the best option always is to improve the sprue system. So as opposed to put a tiny sprue opposite to the heavy part of a casting, put a bigger one more near to the heavy part. And this, in most cases, will help to minimize the problem. The more susceptible the alloy is to shrinkage porosity, the bigger the sprues will come, the shorter they will become, and in extreme cases, we will also use multiple sprues to optimize the situation. Another option can be to increase flask temperature. This is again a result from computer simulation, where we are asking the program to simulate the porosity in the casting. You can see, again, a test item here with a heavy section here and the feed sprue attached opposite to the heavy section. And you can see that at a low flask temperature, the simulation, and the reality will confirm that, will reveal shrinkage porosity on typical locations. And if we increase flask temperature, the situation will improve. This is the other way to approach the problem, but you have to be very careful because higher process temperatures are not always the right solution, as we will see in the next minutes. Give me a second. Yeah, we're already coming to the second type of porosity that I want to talk about, namely gas porosity. Again, sterling silver is a good example here because it's very prone to gas porosity. Why? Like all molten metals, you can dissolve a lot of oxygen in the molten metal at high temperatures. This is indicated here by this diagram where you can see the amount of dissolved oxygen as a function of temperature. So in this part here, we are above liquidus temperature of pure silver in this case, And this area here indicates the amount of oxygen that we can dissolve in the molten metal. As opposed to that, when the metal solidifies, this small area here indicates the small amount of oxygen that we can dissolve actually in the solidified metal. So what is happening with the oxygen when the metal solidifies? You can see it on this ingot here. The gas tries to escape, and we form typically spherical gas pores. How can we try to avoid this? There are basically three categories we will quickly talk about. Contamination of scrap and raw material is a typical reason for gas porosity. Poor melting and casting process parameters is a second typical reason, and reaction with the investment is a main third reason for gas porosity. Going quickly through these three different options that we want to talk about. Again, a case study here with some big gas pores on a ring shank for sterling silver. If you look at, with analytical equipment, with a microscope on microsections, we can look into the nature of the defects, and in this case we can see a lot of impurities, oxides, near to these gas pores. So very probably in this case, the defect was caused by the usage of contaminated scrap material. Scrap material, I don't know if you can clearly see it on this photo here. This is a tree that has been pickled after casting, and where the as cast items were chopped off here. So these are the remainders of the feed sprues, and the surface of the tree looks shiny because the tree has been pickled. But if we broke up the tree and looked inside the main sprue, you can still see a lot of contamination, dark colors here. So the pickle is not sufficient to clean the sprue after casting. It's an important step, but it's not enough to just pickle the tree or blast it. So cleaning the scrap is important. We'll always start with the blasting, pickling, and tumbling process so that the sprues are shiny and look clean, but then the recommendation always is to go into a regranulation step, which involves remelting and degassing of the metal, and that will help to reduce the amount of gas that may be dissolved in the scrap material. Yeah, it's a process that can be done on dedicated equipment, like a granulation equipment. It can also be done right before the casting process in a casting machine. So typically what we recommend is to increase the temperature 50 or 100 degrees C above the typical casting temperature. The graphite crucible will generate an atmosphere that will take out the dissolved oxygen from the molten metal. Applying a vacuum or an even more reducing atmosphere can be also done on certain types of equipment. We will observe the melt and see the gas bubbling out. Then we can reduce it once the melt is quiet and then go to a usual casting or graining temperature. So a low oxygen level can therewith obtained also for properly recycled material, and that will translate greatly into improved quality of the casting. Poor processing can be another topic during the casting process. Here is an example for, I think it's 18 karat gold, some pinholes here on the surface. We don't want to blame all defects always on poor equipment, but there's a lot of old equipment still outside where we have open melting processes, where the flask is not in a protective atmosphere, or even if it is, we may still have an open melting process on top. So nowadays, we usually work with closed chamber machines where we have a protection of the melt in a closed chamber where we can work with protective gas and vacuum. And of course, we have a closed flask chamber where we can also work with protective gas and vacuum to maintain a very clean atmosphere, an oxygen-free atmosphere during the melting and pouring process. we can differentiate between 3 different subsequent process steps in the casting process. First, the melting phase, then the pouring phase itself, where we have to load the flask at a certain point, and then after pouring, when the stopper rod has been lifted, the melt has poured into the mold, then we have the cooling phase of the flask, and we have to take out the flask at a certain time. So just very quickly here, to focus on these 2 steps, which are sometimes not giving enough importance to. When do we load the flask into the machine? When we take it from the furnace, it's full of air. We should put it into the machine early enough to allow the atmosphere to be cleaned, to really take out all the air from the mold. If this is done early enough, like 1 or 2 minutes before pouring, then this is usually sufficient. Casters are sometimes afraid of the drop in temperature by waiting so long with the flask in the machine, but we can tell that by many measurements on the flasks that this effect is really minimum, and the benefit instead is that we have a clean atmosphere in the flask before we pour. Just the same, after casting, we should not take out the flask immediately from the machine in order to accelerate the process. It will greatly improve casting quality if we wait and keep the flask inside the machine for a while before taking it out, benefiting from the good atmosphere that we have in the machine. So up to several minutes can be helpful, even if it means maybe less flasks per hour. So we have already talked now about these 2 aspects. I have a third one I want to talk about now, a reaction with investment. Now, this is a case study here where we observed on the surface or also on the cross-section actually more irregular shaped pores, where we could probably think that this is shrinkage porosity. However, the item was not particularly bad sprued, so we would not necessarily expect shrinkage porosity in these areas. And indeed, if we look closer, especially on a microsection, we can see that the porosity focuses or localizes on the surface near area and also contains some spherical pores. So this is a typical feature of gas porosity caused by reaction with investment. I have another video here running. It's actually a cross-section through a flask where we have seen molten metal pouring into the mold, and I have to restart it because it was really too fast. So it's a cross-section in a simulation through the flask. This is part of the main sprue. This is the feed sprue. This is the item that we cast. If we let the metal flow inside, you can see everything here is at high temperature now, about the pouring temperature, and the blue color here is the investment material that surrounds the as-cast part. And what you can observe now, if I let the video run, you can see temperature increasing a lot in the surrounding of the as-cast part, especially in some areas where heat dissipation is restricted. The flask, the investment material can become very high in temperature in the direct surrounding of the casting. And the investment material is only stable up to a certain temperature. It will also depend on the metal properties, whether the metal is reactive with the investment or not. But in many cases, we can trace gas porosity back to reactions with the investment caused by decomposition of the investment material. It releases gas, it's oxides material. If they are decomposed, oxide or oxygen will diffuse into the molten metal, especially in the surface near regions. This will create gas porosity caused by reaction with investment. High process temperatures are not always the only reason for this type of defect. We have to control the investment material that we use. Investment beyond shelf life can contribute to the problem. A poor burnout process can contribute to the problem. Temperature control of the burnout oven can be an issue. So there are several aspects that have to be kept in mind in relation to this defect. As a general rule, I want to close with some two extreme cases here. When we cast filigree items, lightweight parts, where we typically use high or medium to high flask temperatures, yes, we can do that. If we pour into molds at high flask temperature, there's always a risk for reaction with investment. But if we want to fill the parts, then there's no way out. We have to do that. And the risk for reacting with the investment will be, in this case, low, because the volume of the more filigree parts is not so high. So the heat up of the investment will be less. So in this case, going to medium to high flask temperatures is mandatory. We have to obtain the fill first of all, and then we have to look at the quality of the surface. And yes, we can improve the fill process by putting overpressure in the melting chamber to assist the fill, to push the metal into the cavities of the mold to obtain optimum fill. We can also assist by putting a vacuum in the upper chamber, which will effectively evacuate the mold too from the inside and the top part, from the top chamber and from the flask chamber, and that will also allow the metal to better fill the mold. So this is let's say a set of process parameters that we will obtain if you go to cast very filigree items. If we, opposed to that, if we cast more heavy parts, we have to be more careful. More heavy parts will be more prone to gas porosity caused by reaction with the investment. So it's always a good idea not to exaggerate, not to put a vacuum also in the upper chamber here. We will just maintain an ambient pressure in the melting chamber. This will create only a partial vacuum then in the inside of the mold. So when the metal pours in, the metal flow will be more gentle. There will be a back pressure on the molten metal when it is pouring inside the mold. This will reduce turbulences, and it will lead to less reaction with investment. In combination with a low flask temperature, this is a good idea to avoid reaction with investment. So I'm already coming to the end. Again, this was training material. Sometimes it's just good to go back to the basics before thinking about innovation. So there's a lot of publications outside summarizing these and other parts that we should sometimes remember. Already JTF proceedings were mentioned by Massimo earlier, so they are available online. We have proceedings from the Santa Fe Symposium over, I don't know how many, 20-something years by now. So there's a lot of literature outside where you can go back to the basics and, of course, back to research. There are handbooks on investment casting and casting defects published by the World Gold Council. So a lot of useful material is out there that many of us should refer to in our daily practice and routine in order to avoid defects, to improve quality, and reduce costs. Thank you very much.